Hello, welcome to this tutorial. I'm going to do this in one take, if possible. Here is some data I had from the water waves practical, in which I filled the tray to different depths, measured the time taken for 5 traverses of water waves from one side to the other. You can see here I've got a number of depths measured with a ruler, a number of times measured with a stopwatch, and the length of the tray. Now, just a few things on presentation before we get down to data analysis. So I measured these to the nearest millimetre, so really I want to show these depths to the nearest millimetre. Okay, so we need to force Excel to show that first decimal place. So you can use these controls up here as I'm doing. We can do that the same thing for the times, so I want them to the nearest hundredth of a second. I also like to center align all my data like this. This column also needs to be to the correct precision. Okay, by the way, I found the average using Excel's average function. I will be showing you a number of functions throughout this. Average is a particularly useful one. In order to use it, you simply type in average and then select the range for which you'd like to find the average. If I center align these titles, and then because I want this title, time for 3 traverses, and it's actually 5 traverses, over the whole set of data, I'm going to click merge and center like so. Okay, ignore this. I can go for now. So first thing I'd like to do is do some error discussion. So obviously I've got 3 repeats for each time. With a small set of data like this, rather than using the standard deviation, I would use the range over 2 to estimate the uncertainty. So how do you do that? Well, you can use the max and min functions in Excel to give you the range easily, and then divide the whole thing by 2 to get to what is sometimes referred to as the spread error. Really, it just gives you an idea of the uncertainty, the absolute uncertainty on your measurements. I'm going to increase the number of decimal places here. You can see that for this set of repeats, because they're all the same, I don't have any particular spread error. I could use the largest value that I have here, but we'll find out that actually the main source of uncertainty in this investigation was the measurement of the depth and also the length of the tray, mainly due to the properties of the tray I used. Okay, so it didn't have a constant depth, and where you take to be the end of the tray is open to interpretation. So I'm going to label this column absolute uncertainty in 5t, where 5t is the time for 1 traverse. Center align. I'm going to shade this column grey. It's just to demarcate it as an uncertainty column. Okay, next we want to divide by 5 to get to the time for 1 traverse. So we'll call this t, just to shorten it. And strictly speaking, what I'll do, averaged for 1 traverse t. Okay, so that's going to equal this cell divided by 5. If I copy that down, now you can, I learned this shortcut not long ago. You can drag it down like that and it'll copy all these values, incrementing the cell you're using by 1 each time. You can also simply hold your mouse pointer over this bottom right hand corner and double click, adjust the precision so that we go to the nearest hundredth of a second, center align. Okay, so that's the time for 1 traverse. Now the absolute uncertainty, so the absolute uncertainty in t, in seconds, is going to be plus or minus a fifth of what it was before. So it's going to be f2 divided by 5. Again, adjust that like so. Okay, again, let's fill that column just to make it clear. Center align. Okay, now I want to work out the velocities of the waves. I have a time taken for one traverse and the length of the tray, so I can work out the wave speed, well, let's call it V, in meters per second. I don't know a quicker way of doing that, not in Excel. Wave speed. So it'll be the average time, the distance, sorry, of the which the wave travels, which is the length of the tray, and I want to ensure that all these cells here use this value B13. Now, if I just leave B13 in the formula, it'll carry me down B14, B15. So I want to keep it in row 13, so I put a $ in front of the 13. Okay, so we'll see how that works in a minute. Divide it by the time taken for one traverse, which is in G2. So that gives me the wave speed in, apologies, centimeters per second, because this is in centimeters. Drag this down, you can see that if I move down column I, B13 is used for every instance of that calculation. Again, let me just, we've got the time in 3 significant figures, distance to 4, so let's make 3 is a suitable number really for that. Let's go with that. Okay, so center align. So in calculating the wave speed, we've done distance divided by time, so we need to use the law of error propagation relating to the product or the quotient of two quantities, which is to add the percentage uncertainty. So what I'm going to do, I'm going to work out the percentage uncertainties or the fractional uncertainties in both time, which is going to be the absolute uncertainty divided by the mean value, and then I'm going to add to that the fractional uncertainty in the length of the tray. Now, when I measure the tray, given what the tray looked like, I'm going to say that ½ centimetre is a good or a suitable uncertainty. I'm now going to divide that by 87.5, and obviously again I want to ensure that that stays fixed in row 13. Now that will give me the percentage uncertainty in the velocity. I then multiply by the actual velocity to get back to an absolute uncertainty, like this, and then adjust the precision again. That'll do, I think. Okay, so you can see that these are significant, mainly due to the absolute uncertainty or the percentage uncertainty of the length of the tray. Center align these. Absolute uncertainty in V in centimeters per second. Okay, I'll leave that for now. Again, fill that column. Okay, so what have we got? We've got wave speed and we've got depth. Now, the relationship, I'm assuming, is a power law relationship. What that means is I'm going to have to plot a log graph. I'm not going to go into the details right now, but if you have a relationship, wave speed is equal to a constant times depth to a certain power. In order to calculate the power, we're going to have to plot a log graph. Now it turns out for V equals KD to the power A, if you plot a graph of log V against log D, the gradient of your straight line should give you the power. So I'm going to have to work out these log values. So that's what I'm going to do in these two columns here. Ignore what I'm doing, I'm just doing this so that things aren't all okay already. Okay, log D. So these are my log D values. I'm going to use the natural log function of Excel. with my values of d. Work these out. I'm going to leave a space. I'm going to work out the values of log v. Incidentally, these are going to be dimensionless. Log of v. So what am I doing here? Just log of I2. Calculate these. Again, adjust the precision to suitable level. Okay, now let's just center align everything here. Uncertainties. Now you can use Taylor expansions to justify this, but I'm just going to tell you the result. For a logarithm, the absolute uncertainty in a logarithm is equal to the absolute uncertainty divided by the value you had in the first place. So in this case, delta v over v. That gives us the following. Sorry, so apologies. For depth, it's going to be the absolute uncertainty in depth, which is, well, again, given the properties of the tray I was dealing with, I would suggest that 1 millimeter is appropriate. So I'm going to go 0.1 divided by 0.6. So that's my absolute uncertainty in log of d. And my absolute uncertainty in log of v is going to equal the absolute uncertainty in v divided by the value of v. Again, I'm going to make sure everything's center aligned, and then these and these do not really need to be to any greater precision than that. I'm going to, because of some of these errors are so small, I'm going to add in just so we can see what we actually do have for some of these down here. I'm going to shade both these in with the grey fill, just to show that they are uncertainty columns. I've now got enough to go ahead and plot some graphs. So I'm going to stop here for part one. I'm going to neaten these rows and columns up a little bit, capital letters and superscripts, and then I'll be back to plot some graphs. Okay.